recording is functioning. And I'll share my screen. Oh, I've been silly. Hold on, I'll need to actually quickly jump back out of the column back into it. It doesn't play nice with this web browser. Be back in a flash. Howdy again. Okay. Nice. Excellent. Okie dokie. Cool. I'll start with the attendance survey, and then I will make my spider a bit bigger so people can see, and then we'll play on with some machine learning things. Before that, I guess I'll do a little poll, because I can. I'll do the poll in the Discord thing, so you can do your little reacts there. I'll ask how many people have actually got set up things that they're going to try and follow along with. So I guess just TensorFlow installed somewhere, or using like Google Colab. I think you can do that as well. So let's see. People are along today. There we are. A little poll in the Discord, and I should have a attendance survey in just a moment. Our poll has many indecisive people because it has no responses yet. Let's see. Dun, 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 dun. Organization. Attendance. Wonderful. Okay. Cool. So I will grab this. There we are. Sorry. Okay, cool. So it looks like some people are going to try and follow along today. Awesome. So sorry again for this little bit of a slow start here. I was in a staff-student meeting for ages, and then kind of got this jumped on me. Because my department apparently is going to no longer exist next year, and they're merging it with 3 other departments, so that was an exciting revelation. But, and before you panic, it's not like a, well, probably not one of yours, unless any of you are studying in biomedical sciences, animal and plant sciences, or molecular biology. But, yeah. Anyways, the form, the little link that I've sent there is just an attendance thing. It'd be excellent if you could just fill in your name. It's best when you make it like the same name each week, just so we can keep track of people showing up. That's good for when we want to go to people for like funding purposes. We have a lot more sway when we can show them, hey, look at all these people showing up to our society. Give us more money. And we always want more money because we can do more cool things. So it would be excellent if you could fill in that. And then we will jump on with things. Cool. Wish to restart now. Sure. Go for it, Spider. Hopefully it'll be bigger. I don't think it restarts on its own, actually. Oh, does it? Did it surprise me? It surprised me. Awesome. Okay. So, for the people who are on the Google Meet, first question, can you see my screen? Second question, can you read the screen properly? It has some random Python file on it. It's not related to what we're doing today at the moment, but... Awesome. Cool. Sounds good. In that case, then I will hop over to the folder that I've got things in. Oh yeah, for the people who are looking to follow along today, you might find it useful to download the data that I'll be working with. Recording, yes, things are recording and they look decent, so hopefully we'll be all right. Good shout. Societies, bionics, arms and glory. Gosh, that's hidden away a long ways, isn't it? Oh, I see, I have to open a particular file. Well then. Here's what we'll do. We'll take a look at preprocessing there. This is the file we'll eventually be writing, but we're going to work through it basically from the ground up in another file, and I can call it something different. Preprocessing. Why not? Very helpful. Probably don't need 2.pys at the end of that. And then the data that we'll be using today, you can find on our GitHub repo, or GitLab repo even. So I will send a link to that as well. Arms and Glory. Thomas is in charge of the name of this repository, so if you have any strong emotions about it one way or the other, you can direct them towards him. Lovely. Cool. So I'll grab that link, and I'll fire that into the Google chat, and also into the Discord. And our specific data here is hiding inside of this folder called /data, and we're going to be using the final data here, which was collected from Thomas when we strapped him to a Myo band and had him move his hand about. So that is where that has come from. Excellent. Well, with that out of the way, let's double check that I'm in the right folder. I am not, of course. That is fine. We can get there. So I want to move documents, university, miscellaneous, and societies, and bionics, and arms and glory. There we are. Okay.
Very organized. Mine does not look like that.
Well, parts of it are very organized. Things end up very far down in folders and take a while to get to, but I appreciate I fooled you into thinking I'm organized. Lovely. Okay. Awesome. So with all of that out of the way, and given that our data is here, let's think for a brief moment about what the big steps are going to be when we're doing our machine learning. So what these machine learning algorithms can do, in our case we're going to be probably looking at LSTMs, which are long short-term memory networks, very helpful acronym. Those are a type of neural network, so they can learn on their own, hence the machine learning part of things. And the way that they learn is by, they have these weights in them, which are just like these numbers, because it's all a mathematical system. And what you do is you take some sort of input, so in our case it's going to be data from a Myo band, you shove it into the network, and the network spits out on the other end some random set of numbers, because your weights start randomized. But then you tell it, no, bad neural network, I want you to spit out something that looks like this, and you give it a good example of an output that you'd be expecting. So for example, we're going to try and be classifying this EMG data into, well, this is a fist clench gesture, or this one is a finger up and down gesture. And we're going to try and distinguish those based on the signals they produce on the EMG. So we'll be telling the neural network it should be a finger wag gesture or something. And then it will say, oh, okay, I understand. And it will go back, and through a process called backpropagation, which we won't have time to dive into in terrible detail because it's some complex maths, but if you're interested, there's the keyword for you to search is backpropagation. That goes back through, and it says, okay, if this is the expected output, how do we get closer to that? And it works backwards through the network to update all of those weights so that if it were given that same input again, it would be closer to the output that you would like from it. And essentially, by doing that process over and over and over again with a bunch of different data, saying, here's the input, here's what I want out of you, try and get closer, and then repeating that process, that's how you can train these machine learning algorithms, particularly neural networks, I guess, more specifically, although there are other algorithms that also are trained in a very similar way. Excellent, but for the algorithm and network to be able to do that, you need to hand it data that's very nicely prepared. Okay, so our data, good question, Ben. Our data we're doing is actually just the final folder itself. The final Mark folder is the stuff that we actually got from Mark, who is our pilot for our arm prosthetic. But that was the first data we collected. We kind of collected it poorly. That's on me and Thomas. So we had to recollect it with more data, more repetition the second time. So we're using just the final folder, not final Mark. But good question. And that actually ties into the point that I was making as well, which is because machine learning algorithms just take the data that you give it and try and make predictions from that data, the results you get out are only as good as the training data that you put in. So if you give it rubbish, you're going to get rubbish out the other end. Our final Mark data was not rubbish, but also not excellent either. So the best we could get, and we didn't finish with it a whole bunch, but the best we could get on like our accuracy for our neural network was around 60%. compared to what we've eventually gotten up to, which is about 95%. Now, granted, our 95% doesn't translate immediately into like live time gesture recognition because we need even more diverse data for that, actually, because we did all of our recordings with just the Maya band in one exact position on Thomas's arm. We never took it off and put it on a second time or anything like that. So, summary there is the better your data is that you put into machine learning, the better your results at the other end are going to be. Sometimes you, the person, needs to do work to try and make that data better than when you very, very first recorded it, process it a little, and that'll be the bit that we'll be focusing on today. Yeah, excellent. Cool. So, on that note, it's actually probably a good idea to take a look at and explain the data that we did collect so we can understand that, and then understand how we need to change it going forwards. So if I go in and pop into data, and then our final data folder, here you can see a set of files, hopefully, that are titled EMG data and then dash G some number, where G is the gesture number. So we did 8 different gestures that we collected information on. Let's see if I can make that a bit bigger. Yeah, there we are. So 0 through 7, so 8 different files. And we recorded like the names or kind of the human meaning for these gestures here in this text file. We recorded a video at some point that would have been more helpful. So if you go and do this in the future, be sure that you keep very close record of what data corresponds to which gesture and what that looks like in the real world. Because, for example, if you read the words wrist side to side vertical, I don't know about you, that might not mean a massive amount to you right off the bat. That's a bit ambiguous. So it's good to pair these things with like pictures or video just for your sake later on, which is something technically we've done, but it's not organized here. So that's a place where you can improve on what we've done for sure. Cool. But, so that's what this little gestures file looks like. We won't be using that today. We use that in our other file in this repository that does live classification of things, which worked decently well. If you'd like to see, actually, I can shamelessly self-promote myself /Bionics by showing you the blog post to it. Okay, view all posts. I think it's like the 4th oldest one now. It was written ages ago. I'm going to, by the end of this session, also publish another one of these posts that talks about what we've done today. So that should serve as like an additional aid to watching this video back over. But here's the part 1. Here's where we talked about what we were doing. Talked about our data collection. Here's our results. You can watch this cool video of us live picking up gestures from the Maya band, which is pretty cool. It works all right, and there's definitely lots of ways to improve it, but it works really well on the training data. So that means that realistically what we probably, so it works really well on the training and testing data. So we'll get into that distinction like tomorrow. But I think what we need basically is better data. If anyone is curious though, there is the link, and you can check that out whenever you are curious. Sitting in my living room with Thomas there. Wonderful. Back in the good old pre-COVID-ish kind of days, before the strict lockdowns. Cool. All right, so let's take a look at this actual bit of data here. Has anyone seen CSV files before? .csv? They're decently common with like spreadsheets and things. What it means, what the CSV stands for, is comma-separated values. So as you can see, this file, it's a text file, which is nice. We can read it, and it's very easy for Python to read as well. It's a series of values separated by commas. Wow, I wonder where the name came from. But you can read this a little bit like a spreadsheet. In fact, you can import it directly into spreadsheets. Am I going to be bothered to do that? Sure, why not? Might make it easier to look at. Each thing separated by a comma represents one column, and then each line is just another row in the sheet itself. Goodness, Office software is slow, isn't it? Yeah, okay. Well, it's a bit small, but here you can see, maybe. There's like the time here, the time column, then you have all of your EMG columns, and then farther over you've got the other columns. And each of them has one value inside. So that's what it looks like if you load it into a spreadsheet program, but we want to load it into Python. So how do we do that? Well, actually it's probably worth exploring the structure of this data slightly further as well. So each one of these files, I think I mentioned earlier briefly, is one gesture. So that means for all of this file 1, I've had Thomas clenching his fist, for example, or I guess gesture 0. So for all of gesture 0, I've had Thomas clenching his fist. But because you need lots of repetition so that the machine learning algorithm can pick out the noise from the important parts of the data, we've repeated each of these gestures, except for one of them, 30 times. The one that we did not repeat 30 times was repeated 20 times because Thomas was avidly convinced that he'd done it 30 times and he did not. But that's all right. So also, something that the ARM team is working on at the moment, I think, actually, is a better data collection program. So it could tell you how many repeats you have left to do, and you can go back and add them. So if that's something you're interested in, get in touch with either me or Thomas, for sure, or someone on the ARM team. But each one of those repeats, so each time he's clenched his fist and released it, and then clenched it a second time, and then a third time, and then all the way up through 30, each one of those is separated by a special line in our data file. So if we scroll down, we see a whole bunch of numbers, and then we see this big break here, where it restarts the time back at some small number. This is in milliseconds, I believe. Yeah, so about 2 seconds for each one of them. That makes sense. So this is the time in milliseconds. Then here are all the data values. But what it does when it splits a repeat is it restarts the timer. So you can see here it starts back down at like a low number, 3 milliseconds here. And says repeat 2. And then the rest of the columns are empty. And then it will do that every time you reach one of these divides. So there's another one, and then another one down here. So that's how these files are structured. And it's our job kind of to break this up and isolate each one of these repeats individually inside. Of course, if you're feeling really dedicated, you could go through and like copy paste, I guess what would that be, 30 repeats across 8 files, 240 different blocks of data and stuff you could copy around, but that sounds terrible, so we're going to do it in Python. And just as a quick disclaimer, and again I'll have this up in the written bit, I've already written it up part of it, if you were doing this again, I would not go with this approach of just putting in little dividing lines, because that's much harder to process than lots of other approaches. If I were you, I would have had, say, like instead of time, or maybe between these first 2 columns, had a column that was just for like repeat number, and repeat number would just start at 1 and then go to 2 and then go to 3. Because as we'll see in a second, some of the tools that we'll be using have very easy methods to group things by the value of a column, but it's tricky because it's not very common to find these weird rows in the middle of the file. But that is enough word soup. I think we can probably hop over to doing some Python code. Before I do, though, I'll do a quick poll just to see if anybody have any high-level questions before we start. Questions about ML. And feel free to ask them either over microphone or in either of the chats. I'll try and keep an eye on them. The poll is now up on Discord. Cool. I'll get that there. Excellent. It seems that there are no questions immediately. If there are, there we are. Might be off topic, but just a way to calculate how long a training phase will take. Ooh. It really depends. In my particular model, on this particular computer, you can calculate it just if you do the training phase, and then you record how long it is, I guess. So for example, on this computer, when I'm training the convolutional neural network, it takes about 3.3 seconds to train a model up to most of its accuracy level. We'll take a look in detail how you can like analyze the outputs of machine learning in our third session. That'll be kind of what that's dedicated to, is evaluating and improving things. I don't think there's an easy way to predict, oh, this will take this amount of time before you try it, although you can get an intuition for it. So I don't think I can give an exact answer to that, unfortunately, but I think it's something you'll get a bit of a feel for. Depends a lot on the hardware you're using, what acceleration you have turned on, how much data you're going through, what model you're trying to train. Lots of things like that. But yeah, that's a good question. I think it depends on a lot of factors. Awesome, cool. Are there any other questions that people have? If not, you can vote in the poll, or if so, you can vote in the poll. Or I'll just head on in a second. Either or. Cool. Okay. It's very easy to see when people have questions in real life because you can, like, see on their face, or maybe they raise their hand, but it's always tricky. Oh yeah, you can even raise your hand in the Google thing, so if you ever feel like it, feel free to do that, and I'll try and keep an eye on it. But for now, I think what we'll do is head on to actually writing some Python code. So, starting off, we're going to want to import a couple of things, because while Python's an excellent language with lots of nice things built into it, it wasn't really originally designed to do statistics and machine learning and all of this. So that's kind of been grafted in by a couple of different libraries that are going to be important for us to use. So we will start with a library called pandas, just like the cute, cuddly bears. Pandas. And then usually people shorten these imports, but keep them qualified. So they'll do like something like as PD. So then we can do like PD dot whatever we'd be using from the library. So that's a pretty common import that you'll see. And we'll talk about what pandas offers us in a second. Long story short, the biggest thing it offers us is a data structure called a data frame. They've nicked that from the R programming language, I think, which is something meant for statistics. It's basically like loading it into a spreadsheet, but in Python, because you can give things, well, it's a table of columns and rows, and you can name the rows and name the columns and get data really easily out of it. So it's a bit like we're importing our own special little spreadsheet, and that's called a data frame. So this gives us data frames. And then we're going to import another library that's kind of tightly related to lots of this machine learning stuff, and that's called Numpy. So as you can maybe guess from the name of that library, it has to do with working with numbers. So Numpy offers a load of high performance like matrices and arrays, and ways of doing maths on those very quickly that's like hardware accelerated. So this is part of the reason that libraries like TensorFlow, which uses Numpy heavily, can actually run quickly enough to be useful at all in Python, because by its nature, compared to something like C, which is, for example, what Numpy is written in, Numpy is mostly not written in Python. Python's very slow, so sometimes you'll run into issues with performance, and so Numpy basically helps make it a tolerable level of performance when we're doing machine learning things, which is pretty important because, as Paul has kind of hinted at, sometimes training can take a really long time depending on how much data and how big of a model you're training. Awesome. So, yep, this gives us performance and tools to do with numbers. So, helps with numbers. Helps work with numbers. I think I'll probably lighten up on writing these explanatory comments because there's not much point of them when I'm talking as well. So, oh well, just wrote the first one and yeah, I got in the habit of it. Okay, so the next thing that we'll probably want to take a look at is if all of our stuff was in one file, if we had one big data file, which you could do, by the way. So remember earlier when I said if you could perhaps separate the repeats more easily if you just had a column that said which repeat every single row belonged to. If you also had the same thing for gestures, you'd have one giant CSV file, it'd be a one-line Python code to load all of them in. It'd be fantastic. I did not do that because I did not have the foresight to think about that. When we were collecting this data, that was long before we'd any written this code or the code to actually do machine learning on it. But learn from my mistakes. If you'd want, you could have put all of these into the same file. Since they are not all in the same file, we're going to need to do some file operations and listing all the files in a directory, which we can do with the OS module. So that's what that one is for. And then the last one, I've kind of tossed this in because it's an interesting tool to be aware of. And I used it the first time I went around writing this code. There are definitely other ways to do it, but this is a cool one. This imports the regular expression library. Both of these, by the way, both of these modules here are built into Python, so you'll never need to install these. These ones up here, like pandas and numpy and things, those ones you might need to install. Awesome. Cool. And if people are curious about the install, and if we have time at the end, I'll be happy to go over that. You can do things like setting up virtual environments, which is kind of neat in Python. I only learned how to do that relatively recently, which is probably a bad thing to admit, but oh well. All right. I think before we start trying to load all of these gestures, we should probably focus first on loading just a single one, because that would be useful. So we can focus on loading a single CSV file and then splitting it up in the proper way, so that we can have every single repeat as its own row. The end structure we're going for, if you can imagine it briefly, is we want different rows of our spreadsheet to have basically two things. It'll be more than two columns in the end for a reason you'll see in a bit. But we want each row to have, here is the EMG data, so the raw data from the Myo band. And here on the other side is the gesture it's supposed to be. That's the input and the output for our machine learning algorithm. So those are the important bits to have. So we're going to try and turn this whole mess of data into single rows for each repeat. Cool. Okay, so to start off then, let's define a function for reading the repeats. And we'll build on this as we go. So read repeats. And I'll just give it a file name, and then we'll just do the simplest possible thing we can. So we're just going to return, and then here's a lovely little function for us. Here's where you could do it all in one line if it all were in one file. Read underscore CSV, and that's built right into pandas. And you can just give it a file path and a whole bunch of little options you can see there. Ours is going to be very simple. We're just going to load the file name. Wow, look at that. If only that were all we had to do. Wonderful. So let's take a quick look at how that actually runs. Hello, Spider. Would you like to cooperate today? The answer is no. That's fine. Cool. So we'll go ahead and run that up here. And Variable Explorer is going to be nice as we go along. And I'll run read repeats. Now here's the difficult part. You're going to have to know the relative path to your file. Because I know that I've switched to this directory here, the Arms and Glory directory, I know the relative path to it. It might be a bit trickier if you're trying to do this in Google Colab or something. But here the path is from where we're starting, data/final. And then we're going to give it a specific file like EMG data. We'll load the first one. Why not? Trying to think what it is called. EMG data-g 0.csv. Lovely. So there's my file that I'm going to load, just the first of our data files. And we'll see what it looks like. Wow, there we are. That's quite a lot. I wish this would let me make that a bit bigger. Let's see if I can hide a toolbar. Is it the file toolbar? Well, that was not the one. Yeah, you have to forgive me for not being intimately familiar with Spider, and it's even harder to work with when it's really big like this, but that is all right. Yeah, I can't move this to be any larger, unfortunately, but that's okay. Hopefully we can manage. What we can see here is our data frame. So we have our first column, and it's a bit wrapped. Boy, that is properly hideous, isn't it? That's all right. We are going to get creative. I'm going to hop in here, and as a secondary thing, our little backup one for where we need more space, I'll open a terminal, Python, make it much larger so we can see it, and from there, import our library, which was pre-processing. Excellent. Okay, and then I'll just rerun this command so we can look at it in a slightly less cramped way. Sorry, that's terribly, terribly wrapped there. There we are. Almost, of course. Remember, of course, when you import Python things, you'd still have to put the name before them, unless you do from the library, pre-processing, import, and then everything, which is what I want to do. There we are. Okay. That's marginally nicer to look at. So here's the bit that we're interested in. Does that show up with decent contrast when it's reversed colors like that, or is that terrible to look at? Let me know if it is terrible, I guess. Otherwise, I'll assume that you can read this decently. What we're seeing here is our spreadsheet shape, or our spreadsheet structure, which is our data frame. And it's cut out the middle bits and some of the columns as well to fit it on our screen decently. But you can still see the important parts. You have like your time in your first column, and you can see we have all the way up from our 0th recording all the way through 3,837 lines. And you see you have all these individual EMG columns here. And we also have at the end of this a whole bunch of extra data. So if we look at our original data structure again, which I think is vibing over here, after our EMG data ends, so there's all of our EMG data. We also have a bunch of stuff about, I think these are the values of a quaternion, which is for like detecting rotations and orientation in 3D space. So the Maya band does some fancy stuff about that, so you can see how it's like oriented in 3D space. Can be useful, not for us. Same with the gyroscope and accelerometers, at least not for what we're doing at the immediate moment. So what we can do is chop all of that data out. We probably don't want to be cluttering up our work with any stuff that we don't need. That's the other thing with machine learning. You want to give it only the data that it's relevant, and not clutter it up with anything else, because it will latch onto anything that it can to find patterns. And maybe that's good. Maybe you just want to throw the kitchen sink at it. But if you want something to learn specifically EMG data, give it EMG data and nothing else. Wonderful. Okay, so what is some way that we can trim this down? That's a good question. So say we take our read repeats here. We're still in this terminal zone. What we can do with these spreadsheets is there's a whole bunch of different ways to access different parts of them. A nice way is you can give it a range of columns that you would like. So just as if you're indexing an array or something in Python, so trying to get like the first or second or third number from a list, you can get first or second or third columns and rows from a data frame. So in this case, we can give the column names. First, the one that we want to start at, which will be EMG0. Note that we're going to be throwing away the time column here, but that's because the gap between them is like semi-consistent, so it almost kind of tracks with time anyways. So it's not really something we need to normalize for. If you had EMG data that was running at different sampling rates or something, you might want to normalize for that and include that somehow and stretch and shrink it so there's a constant like speed of time or whatever, like time per row. But since we're just using the same data everywhere, we probably won't fuss too much with that, and we'll just grab the EMG parts. So I'm going to grab EMG 0 through, and I know my last one is EMG 7. And you have to put those in quotes because those are strings, the titles of these columns. And if you run that, then I will get something invalid. Oh, that's fine. I knew that would happen. Yes, so when you're doing this direct indexing like this, it actually tries to do rows instead of columns. If you want to do columns and rows, you can do .lock. And that's just a way of like accessing things by their label. So that's the label bit, I guess. So in this case, then we give X and Y, or rows and columns that we want. So we want all of the rows. So you might recall this just plain colon thing from other times when we were working with like list slices. Because remember, if I had done something like, for example, :5, this would go from 0 to 5, because it goes from the beginning until the end that you specify. If I were to do it the other way around, it would have started at 5 and then gone to the end of the list. If you do it this way, it goes from the start to the end. So this grabs all of the rows and only the columns that are EMG 0 through EMG 7. So there we are. Now we have a much nicer spreadsheet looking thing. So you can see here it's still trimming out stuff in the middle because we've got like, 3,800 rows. It doesn't want to dump all those on the screen, but we now only have 8 columns, which is exactly what we want. We have 8 channels of our EMG, so that's a good place to start. Let's drop that into our code. So if we go here, we can put it immediately after our read CSV. That should be fine. We can just do lock, LOC, and then grab all of the rows, and then grab just the columns we are interested in, which is EMG 0 through EMG 7. There we are. Lovely. And we'll give that a quick test. Run that there. Run that there. There we are. 8 columns. Just what we're looking for. Cool. And hey, it even almost fits on the screen here. Cool. As a curiosity, can I get rid of that? Certainly can't. That's fine. All right, I'll pause real quick there. Any questions about data frames before we head on? I'll put up another poll in the Discord so you can answer that. Or I'll ask how are people feeling about data frames. Feeling about things so far. Any questions? Anything's tricky thus far? Or are people feeling good? Give me a thumbs up in the Discord poll if you're feeling good, feeling fine. Dun, 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 dun. Cool. Well, one person's feeling good. That's a good start. Cool. Awesome. Since I'm not hearing any questions, I'll probably power onwards. Panda, I like that. That's a good reaction. I'll power onwards, but if you have any questions, interrupt me at any point, and that is fine. So what we've done so far, just to recap, is we've loaded in our first gesture file, and we've grabbed just the columns we're interested in. So now what we need to do is think about how we're going to actually split up these repeats. That is the most difficult part of this code, probably, because there's a lot of ways to do it. The way that I did it the first time around, I didn't like, so I rewrote it all yesterday, or the day before. So it's totally different now. But I think it's a bit cleaner. So first thing we should probably do is identify where the boundaries of each repeat are. So we should look for the rows that have the word repeat in them or that have a bunch of like empty things after them, like this one here. So for example, if we take a look at our first gesture thing and we look at just those rows, so I'll grab up here. We can also grab specific rows, of course, remember? So I want to grab from 115 maybe to 125 because I think that'll contain our boundary. And if I do that, here we are. We can see there's our repeat line right there in the middle. And we see a couple of interesting things about that as well. First of all, EMG0 now no longer has a number, but instead has repeat2, so that's a string in it. So we could look for repeat2. That's the way I did this the first time around. Or you could also look for places where there's a not a number. That's what NaN stands for. So not a number. It's not a number because it was just blank in any of the other EMG columns. So I think this time around, I'm probably going to look for the not a numbers because I think that's marginally simpler. And what we're going to do basically is hunt through this whole data frame, find the rows where there's not a number in EMG column 1 probably specifically, and then we're going to record this number here so we know where that happens, this indexes row. So to start with that, let's pop over here again and store that in a variable called data frame, just df for data frame. That's pretty common. You can also give things more descriptive names if you would like. Might be a good practice maybe. And we will return something new, which we're going to calculate now. So another interesting thing to think about, or to look at, I guess, rather, I'll show it off here again, is with these data frames. So I will store this whole thing, the whole data frame, in a variable here in this terminal as well. So I'll put it in df. If we store that there, what we can do is operations sometimes over like the whole array, so it does things for every single row. So to show off that in a bit less like vague terms, if I do something like EMG1, for example, this will give me just the column for EMG1, but then if we do something on top of that, like put it in a variable or do some operation with it, so I could do like for all the things that are greater than 40, and then it will tell me some of these things are greater than 40, true, false for the others that are less than 40. And you can see that matches up here because all these were 100s and all these are down here are 20s. And then what you can do is use these true and falses to select data out of a data frame. So what we can do is find all the places where it's not a number. We can do that with Numpy, bring in Numpy, so that's np. Ooh, yeah, np should be imported here. And then we're going to do is, not a number, so isnan. And this will tell us all the places where something's not a number. So now you see here, it's false for all those, but that's fine because those are like true things, or they are actual, that was incredibly vague, sorry, because those are actually places where it is not a number. So it's true, or it's proper for those to be false. If we look at a specific part of the data frame, again, where it's, let me see if this should behave. If we look at a specific part of the data frame, again, where we know that there's a break, which is around that place. There we are. We can see false, 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 false. And then we have 121, which, if you'll recall, was our divider line earlier. Yep, here, repeat to 121. There you have a true, which is quite interesting. So what you can do with this very neat bit of data, or this like list of all the places where the not a numbers are, is index another list by them. So this is something called Boolean Indexing. The bit I'm writing up has a link into the documentation for pandas about this. But we can do something like df, and then we're indexing, so we're looking for the values, and then this basically tells us, it'll go through row by row. Wherever this is false, it will not grab it. Wherever it is true, it will grab it. So what this is going to do is return all of the rows in our data frame that have a not a number in them. So it will return 121 and all of the others as well. So if we try that, there we are. There's all of those rows. You can see repeat 2 starting at 121, and all of the ones after that automatically selected. That's quite nice, right? So that's a really good place to start. Then you might be thinking, well, okay, we don't really need all of this rubbish over here, do we? We just kind of want these numbers. And there is, yet again, a very easy way to do that. We just pop on the end of it a dot index, and that will give us only these index values up here. So if we do that, et voila, we have 121, our first boundary, and then all of the other boundaries after that, which is very, very helpful. So let's go ahead and toss that in here. I'll actually just copy and paste that since I wrote all of the code here. There we are. Pop. There we are. Lovely. So there is that. Now, the one last thing we're going to want to do, and this is me thinking forward a little bit. This is the advantage of foresight. You probably have to go backwards and forwards in, well, your actual thinking process to get to this point. But what I'm planning on doing with this list of indices, I'll put it in a list here. So what I'm planning on doing with these is zipping them with an offset. So I'll show you what that looks like. So the list is here just so, well, I'll show you without as well, actually. So if you zip two values, what it does, two lists even, is it will take those lists and it will look at the first item of both of them, then it will stick them together in a tuple. So it'll be like both of those items in one like tuple value, and it puts that in a new list. And it does the next for the next one and the next for the next one. So you're thinking about taking two lists here and you're zipping them together. That's why it's called a zip. And that'll be a bit clearer in a second. So if I do LST, that's what I was doing. And I'll just zip it with itself so you can see that. So you see here, you just get like zip object at, and it gives you a memory location. Incredibly unhelpful. And it makes me upset that it still does that by default. But we can fix that just by converting it to a list, which is something we can actually look at. So here you can see it's combined all the things that we were expecting it to do. For example, our 121, we're combining it with itself, so it's just duplicated every item almost. If I did something like repeat, or range even, range of 50, I don't know, something like that. Unbalanced parentheses there. Oopsie daisy, that is my bad. We'll put in an extra closing parenthesis there, bracket. There you are. Now you can see it'll go up from 0, 1, 2, 3, 4. It just kind of counts along and combines it with that first item from our list. Now, the cool trick we'll be using here to get pairs of these values. So think if we wanted one value in our final list to be 121 and 236, then the next one to be from 236 to 356, and from 356 to 478. That kind of moving in a window of pairs is going to be really helpful, because essentially between these two numbers is a repeat and we want to extract it. Between these two numbers is a repeat that we want to extract, etc. So what we can do is if we zip a list with not just itself twice, but itself shifted by 1. So if we start at index 1, which remembers the second thing in the list, and then just grab the rest of the list and zip those together, we get something like this. And now what you see here is you have the first two numbers, 121, 236. And the next one starts with 236. So from 236 up to 356, and 356 up to 478, and etc. So these are our pairs that we're looking for, which is fantastic. Now, here's where you want to do a sanity check. Think to yourself, okay, are these all of the repeats that we want to grab? And if we go look between 121 and 236, like in our data, well, there's our, well, okay, so keep in mind these numbers here on the side don't actually totally line up with our data frame, because this is 1 shifted by 1 because it's counting the header, which our data frame is not. But the idea is from this location here, shifted forward. From there, yes, you do indeed have a repeat down this way, and that goes all the way until 237 or 238. Remember, those are shifted by 1. So that lines up with what we have here. The problem you might have seen from just that short little example of our first one is we're missing our first repeat, which starts from 0, in fact. Oh yeah, of course, that's why it's shifted by 2, is because the first line is 1. So realistically, in our data frame, this row is considered 0, which is why everything here is shifted by 2, because this is counting it as 2. But we've left out this whole first repeat, and that's something that we probably don't want to do. There's good data here. Additionally, if we take a look back at our things here again, we know that this is the place of the last repeat marker, this, step 3778. That's where the last repeat shows up. However, we're not recording to the end of the list. Like our list is longer than this. Our data frame is, rather. So we're leaving out things at the end as well. Is that reasonable? So here's where you need to kind of know your data. It's important to know the data set you're working with. When we were collecting this data, we started it once we were ready. So the first repeat's definitely important. We want a way to include that. However, once we'd finished our 30, which was this plus the one more at the very beginning, which we can actually probably see by getting the length of the list. Look at that! I remember how to get the length of a list now in Python. We're making steps forward. See, it's 29, so we're missing just one repeat, which is our initial repeat. The last repeat we do want to throw away, because in the real world, that's after we finish doing the gesture, and I just haven't pressed the stop button on recording yet. But I just wanted to end something cleanly, so that's where me and Thomas are deciding, okay, do we do more of these repeats, or should we leave it alone? Stuff like that. So we are fine throwing away the last repeat, so we will not add anything extra at the end here. We would like to grab the first repeat, so we're going to insert an artificial boundary to this list value at position 0. So if we go insert at position 0, this is a list function I may have told you about, we may have seen before, but it's a method, so you do dot insert, and you give it the place you want to insert something, and then the value you want to insert. So I'm going to say there's a boundary at -1, because the first thing we want to include is 0. So this is 1 before the first thing that we want to include. Do that. Then you can see we have our -1 there artificially, and now when we rezip the list, well, we rezip the list without getting the length. Oh, exciting! I wonder if it's not... Oh yeah, it might not be updating that value. So, yeah, okay. If I do list equals the list that I inserted. That's intriguing. I thought that would have updated it, but I guess it doesn't. There we are. So that's what we were looking for. Now we have our first repeat with our imaginary boundary at -1. So we start at 0, and we go forwards up from there. And now if we look at the length of that, of course we're going to be at our 30 that we were expecting, our 30 repeats. So that is all good. Let's take all those words I just threw at you and put them into our Python code. So if we hop down here, basically this index is already really good. We want to add to that this inserting value of putting 0, or putting -1 at position 0. So that's the first thing in the list. And we'll probably want to put that in its own variable now, called boundaries maybe, or bounds even. That's a bit shorter. That'll give us all of our bounds, and then what we can do now is return our zipped together thing. So this is just so we can double check that things are operating as we expect them to be. We're gonna have bounds, and then please go away, Mr. Spider Pop. Bounds, and then bounds shifted by 1. Awesome. Cool. We'll give it a run, and I'll run this real quick. And now you can see, it's printing vertically now, so it makes sense. Yeah, there we are. First repeat, then our second repeat, and then you see this 236 appears again here, 236, 365 or 356, 356. So that seems to be working totally fine, which is good and great and fantastic. Awesome. That is a bit wild. I'll admit that zip is a bit of a interesting way of doing this. The first way I did this, it was longer code, but it was using like a for loop and variables that I was mutating. So I'll do another poll. If people have any questions, now is a good time to ask. How are people feeling about zippy things? There you are. If there are any questions. Cool. Nice. Some people are feeling good. That's good. At least one person. There we are. Excellent. Awesome. Hey, the answers pour in the second I go and guilt trip you all. Haha. Wonderful. Okay, so that's good. We're making good progress. Now all we want to do is extract the rows at each of these places. So you've kind of seen how we do that actually before with data frames a little bit. So when I was over here with my data frame and I wanted just some of the rows, say I wanted this first set of things. This works a bit like list slices in Python regularly do. So just to show off how list slices in Python regularly do, we'll have a variable x here, call it, well, we'll just put in numbers up to 5. If I do x from 1 to 4, which would be from this index here to this index here, because remember 0 is the first one, so it's from this one to this one. It won't actually give us 2 through 5. What instead it's going to do is, because the first one is inclusive and the last one is exclusive, it's going to give us 2 through 4. So you can see that there. That works the exact same way when you're indexing through these data frames. So what we want to do, since this first one, well, actually all of these numbers are the location of a boundary, and we don't want to include the boundaries in our final data frame, we're going to want to do +1, basically, on all of this. So we want to take our starting location +1, so shift forward by 1, and we're going to include the first thing after the boundary. But then if we just put in the boundary, say like 121 as the final part here, that's fine, because boundaries are exclusive anyways, it won't get included. So we'll end up with just the data in between, and we won't grab either of the lines that says repeat. So to show that off in the real world, if I hop back to this, and then here we do something like, yeah, so we'll do a list comprehension. So repeats. Once we're doing a list comprehension, we no longer need to convert it to a list because that's being done automatically. So we want to go through all of our bounds. Oh, and something cool. I think I talked about this at some point in one of our lessons. But when you have tuples, so like these things here, where you have, and it's round brackets in Python, where you have your first number and then your second number, if you do something like, and I guess I can demonstrate this. So if I grab just one of these values, which I can do just by putting 0 there, I'll grab us the first one. Wow, look, a lovely pair. And if we assign that to A, comma, B, that means it creates two separate variables, and you can actually see those up here. A is equal to the first number, B is equal to the separate number, so it kind of splits them up like that. So when I do start and end here, start is equal to the first part of the tuple, end is equal to the second part of the tuple. And what do we want to do for every one of those? Well, we want to go through our data frame. We want to index it, this time slightly differently. So last time we used something called just block that goes by labels. That behaves a bit different than regular indexing. Actually, now that I mention it, so when you're looking at your data frame, like here, this index column doesn't actually have to be numbers. It could be words or letters or whatever you'd like. So what happens when you use the lock thing, LOC, that looks at the labels. So that would, if these columns were named something different, this were like A, B, C, D, we could go through A, B, C, D, and it would work with the lock one. What I lock, so it just has an I in front of it for indexing, or for index, that will actually just do, for the first row, it'll always be 0. For the second row, it'll always be 1. For the third row, it'll always be 2, that kind of thing. So we're going to do iLock here, so it behaves like regular indexing, since we're using indexes here, and we're counting on that slicing behavior. And here, we'll have our start. +1, remember, so we don't include our boundary condition. We want to go until the end, just like that. Wonderful, and actually what I will do is return that so we can look at it and enjoy it and bask in its glory. There we are. Okay, so you see, I have what looks like a list of, and then inside of that list are these data frames. So here's one data frame. That one is 120, well, actually it says at the bottom, so that's 140 rows and 8 columns there. And above that you have a 124 row and 8 column thing here. So that's this one up here, and you have the next one. So we've now created a list of data frames, and they've all been sliced. And you can see where each one of these data frames begins. It's a bit squirrely because it's wrapping here, so... But, like this is the first row, for example. That whole thing is the first row. And this does not have the repeat word in it. If I left out this start +1, we can take a look at what that would look like, just so it doesn't look like I'm totally crazy. If we do something like that, then you can see at the beginning of each one of these data frames, you have your repeat and NaN line, which we don't want in there. And here's another repeat and NaN line. So to get rid of those, that's what this +1 is for. That just excludes that. Starts at the index immediately after. Wonderful. Cool. Looks great. And we can also double check, do some sanity checks here. Do we have enough gestures? So if we grab the number of gestures from this whole thing, length of it, 30. Fantastic. So that's exactly what we're looking for. We now have a list of all these data frames. Cool. Next thing to do here is probably think about how we finally want to output these at the very end. The way that we want to do that is in one big data frame where every single row contains essentially one of these data frames as the input for the neural network, and then a gesture as the output for the neural network. So we'll start by just including these these in a set of rows. So we'll start with that. How might we do that? Well, we can construct a new data frame. So let's look at that process. So we'll do this back to repeats as a variable in our next line. Pop our return. Final time we have to move the return, probably. Pandas, so PD for little panda, and then .data frame. Lovely. So this is how you can create new data frames. There's a bunch of different ways to create new data frames. You can give it data in the shape of a NumPy array. It'll take NumPy arrays and convert them into data frames. Or you could do just lists of values and then list also the names of the columns and it'll fit them in. Bunch of different ways to do it. In the little thing that I write up at the end, I'll link the documentation so you can go explore them all for yourself. The easiest way, I think, is if you give it a dictionary in Python, which remember is a thing of a list of keys and values. The keys are the columns, and the values are just a list of all the values that belong in that column. So if we, for example, created an EMG column, this one's just like a big combined one, so it doesn't need like a number. And we said after that lovely EMG column, I would like all of my repeats, please. Repeats. Wonderful. Go ahead and save that. I'm probably going to load it in here, actually, because I will need to. So Python, let me see if I remember how to do this correctly. I think if you do -I, it loads a file interactively. So let's try preprocessing. Uh-oh. Well, it didn't crash. That's always a good start. And if I run my... Oh boy, that's right, we can do reverse search. Oh yeah, fun fact, if you're working in Python is one example, but also just a regular shell is another one. If you do Control-R, you can do a reverse search. So if I want to, for example, find wherever I'm doing my read repeats thing, I can start typing read repeats. There we are. We can see the last command I ran with read repeats, and I can go ahead and edit that a little bit. Very useful. So there we are. Data frame, read repeats. Take a look at the data frame. Wow, that's hideous, but also expected. Dun dun dun. It was all part of the plan. So here we can see a data frame. It has one column called EMG, which is what we're looking for. And it has 30 rows. Remember that we started at 0, so 0 through 29 is 30 rows. So that seems to be almost exactly what we're looking for. Each one of these is one repeat, except this is hideous and terrible. And if we take a closer look at what's going on here, because this looks probably a bit confusing at first glance. So let's take a look at just the EMG column, which you can get by just doing the title of the column. So there's our just EMG column. Tells us that there are objects inside of here. And then there we are. We can see the same thing that we saw a second ago. And then we also grab, say, the first thing from that. Aha! So that's what we've done. We've nested this data frame here, which is one singular repeat with all of its little EMG components. We put this data frame inside of another data frame, which is kind of not great in terms of how easy it is to work with. It's hard to see the values. It's just a bit unnecessary because all of this information, like 1 through 8, that's still held by the shape of the data. So we don't really need this. These names, I guess, aren't something that a machine learning network is ever going to use. So what we can do is convert these little data frames into NumPy arrays. So you can do that with just 2 NumPy, I believe. So NumPy. Et voila. There you are. Now we have a NumPy array, which is, well, it doesn't do us the polite thing of truncating the middle when it's very long. So keep in mind, these are still the same length of data. It's just data frames intelligently cut out the middle, so you don't have to look at all of them. Arrays don't bother with that. So here you can see, here are 8 values. Those are the EMG channels, and it has these in here 121 times, is it? Yeah, 121 times. So it's the same shape of data, except now it's converted it into an array, so we're not nesting data frames anymore. As a bit of a test of the eagle-eyed among you, is there something wrong with this data if you take a look at it? What is something that might strike you as odd if all of these were supposed to be EMG channels? Anything that people see? Feel free to shout it out. Or type it out, whichever you prefer. There's some trickery afoot. Or, in the absence of answers, I can spoil the surprise. Got a hint? A hint. Well, the hint is, within this highlighted region, one of these things is not like the others. Sorry, I realized that might have been a pretty abstract thing overall. It's about the data. Well, not the values themselves, but the form they're in. Aha! Very eagle-eyed of you, Philip. Yes, you are correct. There are quotations around the first number. That's pretty weird. Why is that? Well, that's because it thinks that's a string, which is kind of not great. So actually, if we go ahead and grab that value, which is 0, 0, there's our 68 thing, and if we run type on that, so you can do type in Python to get the type of it. Uh-oh, SpaghettiOs. That's a string. We don't want that. You can't do maths with strings. The reason this column is a string and none of the rest are is, again, because of my terrible lack of foresight. Remember, this EMG column used to have a string in it. It used to say, on every single boundary, repeat, space, and then the number. So it was originally a string here. So Pandas isn't to blame. It's loaded it properly. We gave it a string, and it loaded it as a string. But that's not something that our neural network can handle, so we're going to have to convert it. Luckily, that is incredibly easy. And in fact, another thing that you might notice, all of these numbers, .0. There are no significant decimal places in any of these. So what we can do is turn them all into integers, save ourselves some trouble, and also fix this string problem at the beginning. Luckily, that's very easy. If I go ahead and take this, get rid of that type bit. So here's our NumPy array again. Here, NumPy, the toNumPy method, takes an optional argument called dtype, which stands for data type. So our data type, and then you can give your data type as a string. And these types come from NumPy directly. It has different types of numbers for you to work with. Long story short, there are different types of numbers that have different accuracies, I guess. So if you think about it, your computer has to store this data for numbers somewhere. And it does that by storing it in some amount of memory. So you can have numbers that are like 32-bit numbers, for example, which is 32-bit binary. So there are 32 ones and zeros that represent that number. So that sets a maximum size for that number, essentially. Or floats are these things. But decimal points are stored also differently in the computer. I won't dive into the details. But the point is we want these to be integers. So we go to int, and we want them to be 32-bit integers just because that's big enough for them all to fit in. And easy for computers to work with. And then go ahead and run that. And now you see our data type is 32-bit integers. And we have all of these things, all of our numbers here, without quotation marks, without decimal points. And in fact, they look much prettier because it's gone ahead and aligned them all for us as well. But that's a bit of a fortunate side effect, I think. But yes, so we solved our little problem there. Now all we need to do is actually just put that into our code. I did that in my original thing by adding this list comprehension. I just put at the end of this data frame indexing to Numpy, and then here tossed in dtype. And then did our 32s. Now, if we go ahead and run this, Python, by the way, I went and looked around for ages. In so many other programming languages, you can do something like :R, for example, in Haskell, and run it, and it will reload the file. Python doesn't seem to let you reload files twice, so you have to close all of Python and open it again. I'm not a fan, but I'm sure someone somewhere did that for a reason. Here we are. Okay, so we can run our rand repeats again. Normally, by the way, you can do this all in Spider. That's how I did it when I was developing it. I'm doing it here because Spider is a bit cramped for us as well. Hey, there we are. That looks a bit better. So we have our one column with EMG again, and now we have our 30 rows still. And inside each one of these is a bunch. It's a NumPy array, even. So again, if we actually grab that thing, so 0 and 0 should work as well here. Just kidding, does not on data frames. That's fine, EMG 0 will. There we are. You can see we get our array back. Very nice. All numbers. Very easy for our machine learning algorithm to work with. So we can just plug that right in the front of it. Cool. That is that. So let's go ahead and pop that into our... Well, that is already in our Spider. So I think that's us mostly finished with this function. The last thing we're going to do, because we're going to need to write a couple of other short little functions, one of which, for example, is going to actually read all of these different files in the data thing. Just kidding. It's hidden it for me. That's fine. It's going to read all the different files in our data file folder. So it's going to read all these CSVs. And it's going to tell this function, basically, you're working with gesture 1 right now, or you're working with gesture 2 or whatever. So we're going to add an argument to this read repeats that says gesture. So we're going to tell it which gesture we'd like to load, essentially, or what we'd like to call it. And then what we're going to do is just add a second column to our data frame. Like we said earlier, it's going to have gesture and what it is. So gesture. Wonderful. And if we take a look at how that looks in terms of an actual output, pop in here, close Python, open Python, go up to read some repeats. Ah, of course, yes. I just added a argument, so I need to actually give it that argument. So this one is gesture 0, for example. So I can say that, and now you can see there's a new column in our data frame, gesture, and it's all zeros, all the way down. Fantastic. And additionally, this could be any type we'd want. So if I wanted this to be the words as well, we could do like clench, fist, or something like that. And that would work just as well. And I think actually our machine learning algorithm would do just fine with that, because we'll see this will change in a little bit anyways. Awesome. Cool. So that is that function done. Well done. That was honestly, I think, the hardest function. It gets easier from here. The next one we want to write is the one that actually loads all these different files. And I'll pause after I write the header of this. If you have any questions, you can feel free to start typing them now, and I will officially do a poll in just a moment. Folder, and we'll give it a path to a folder. Lovely. Okay, cool. And I'll spin up a poll. How are people hanging in? There we are. Let me know in the Discord if you are alive, dead, somewhere in the middle, and how it's going. Cool. Any questions, feel free to ask them. And the crowd goes wild. Okay. Well, I don't see any questions. There we have. One person's responded to the poll at least, so that's good. If you do have questions, again, feel free to interrupt. but I think we'll power onwards then, if there aren't any at the immediate moment. Lovely. Okay, so let's do some thinking. We want to somehow list all of the files in this directory and then find just these ones. So we want to ignore the gestures.txt. So find just these files and then load them all one by one at a time, calling this rand repeats function with each of them individually. So there's a bit that's going to go on here, to be honest with you. But we will start one bit at a time. So first things first, we want to find a way to list all of the files in that folder. How do we do that? Well, that's where our OS module is going to come in handy. So remember we imported that earlier. You can find the documentation for that on the Python official documentation, since this is one of the built-in ones. And we can use a function called listdir. And that will list all the files in a directory. Wow, fascinating, very exciting. So if we go ahead and test this, load emg, yep, that's the one from folder, and then we're going to give it a slightly less specific path this time. We want to just give it data final, data/final, not the whole thing. Run just that, and you can see, there we are, a lovely list of files. We have gestures.txt and then gesture data CSV files 0 through 7. You also might note, that's not quite numerical order. 0, 1, 2, 4, 5, 6, 7, 3. That's a bit strange, isn't it? You might also ask, why is that? The honest answer is, no idea. It might be to do with the last modified date of the files or something like that. It could be totally random from platform to platform. I'd have to double check the documentation of listdir. But the point is, you shouldn't rely on this appearing in something like alphabetical order. And obviously it also includes files that we don't want, like gestures.txt, so we need a way to work around that, if you will. Cool. Okay, so let's think about how we can work around these gestures.txt. So a cool tool that we can use for this are regular expressions. These, if you've never seen them before, probably are going to look like terrible, terrible alien script to you. If you have used them before, then you probably have some fear of them, and that is all right. We're going to demystify them and only use some very basic features. So Regex 101 is a lovely website for testing and explaining these things, so I'll make it a bit bigger here. And doop. Beautiful. Okay, so you can select all your different types. Python, most of these are mostly the same, to be honest. You input your regular expression there, your test string down here. So what I'm going to do is actually copy in all of our files that we're going to be looking at here. That whole mess, copy. And that's the wrong place. Paste it in. Lovely. And now what we need to do is think about how we can select just these things and ignore the rest of them. So regular expressions work a lot like your search box on your computer, just a bit supercharged. So you can do basic things, like if you wanted to do emg data-g-0.csv, that works perfectly fine. And you can see we're identifying, it's matching just one match here on the second line. That's the first thing it matches. If we change our number, obviously, to a different one, that's where it'll find it, which is nice and helpful. You might just think, okay, that's pretty boring, just a regular search. Why is it helpful? The reason it's helpful is because we can also use a whole bunch of tokens and special sequences to create more general patterns, so you don't have to search for something exact. For example, we could search for something that that has just a number here. Any number is fine. That's what we're going to do actually in our final thing. So for that you do \d for digit. Now you can see it's selected all of those. That's really cool, but also quite simple. There are more complex things, of course, here. If you wanted things just to highlight all like file extensions, for example, this would be a bit of a different one. This is just a bit of a tangent almost. For that you can put, okay, I don't mind. Anything at all here is fine. Well, we can do so start at a quotation mark, and anything here is fine in the middle. I think if I do that, there we are. Anything here is fine. So dot means any character. This means any number of times, 0 or more times. So that'll grab everything between these quotation marks. And then we want that to stop at another quotation mark. But we want it to only highlight, for example, or maybe grab separately. So if you want to grab something separately, you put it in brackets for a capture group kind of thing. We could put a dot, except this would be a literal dot because it would be something like that. And then something there, something after it. What this terrible regular expression here means is find everything that's inside of quotes, select the whole string, and pull out the file extension separately. And you can see that here. File extensions are pulled out separately, and the whole thing selected in blue. Luckily for us, we're not going to be doing anything nearly that monstrous, and there are so much more monstrous that you can get. But this is a lovely website for explaining it. For example, it tells you right over here, dot star matches any character except for line terminators. And it gives me this first capturing group, matches the character dot literally, and it explains them all bit by bit, which is really, really nice. What we want to do is a nice simple one, though. So we're going to go back, actually, probably, where I had most of it done. There we are. But what we want to do is grab this number separately, because that number tells us which gesture we're working on. And we want to know, first of all, select just the ones that are data files, which we've already done, and then get out of those data files which gesture they contain, which we can do this capture group there. So now you can see we're ignoring the gestures.txt file, only looking at the emgdata.csv, and out of it we're grabbing the gesture number, which is something that we will use, and we'll pass it to our next function so we can have gesture 0, gesture 1, gesture 2, gesture 3, gesture 4. So there, some fancy regex magic. Feel free to learn more about these. There's a lot more to learn. They're best used in small doses, I think, but they're really powerful, because if you were to write like Python code to do this manually, it'd probably take at least a couple of lines, and this is a decently simple one. But this is all in one very tiny string. So we'll go ahead and copy that, because we know that's working. We've debugged it with this website here. And then we can pop it into our Python, and I'll show you how to do that. Regular expressions are a lot to understand sometimes, especially the more obscure ones. But remember, at their heart, they're just searching for something in a file, sometimes replacing something in a file, sometimes looking for specific parts of that search. Cool. So there's our list of directories. How about we loop through those for a file in that list of directories? We want to look if it matches our regular expression. So re.match is the way to do that. Regular expression strings in Python, you start with an R like this. That's just something that the libraries has you do. There's our regular expression that we designed a second ago, and then right after that, you give it the string that you want it to match in, which is going to be the file name. So that's this file variable up here. And if it matches, print it out for us, so we can print the file name. If we take a look at that then, and go ahead and load this, we now get, whoops, there we are, just our G0 through G, well, 3 at the bottom. But all of our data files, you can see now, no longer do we have our gesture.txt. And there we are. There was that weird thing that Spire inserted there. Don't really know why, but here we are. That's just how it works regularly. Excellent. How do we get this capture group, you may be wondering? Well, a lovely question that is. The way you can do that is by storing the result of this call in a variable. So this is going to be doing something I think you probably saw last week. The weird walrus operator, the one that caused the person who invented Python to stop leading Python development because he hated it and everyone else loved it. Anyways, walrus operator has some painful history behind it for some people, but I love it. Store it in matches. Remember what this does here essentially is it, first of all, takes this, which will be like a true value or something, assigns it to, it'll be some object that counts as true in an if statement, basically. It assigns it to matches so we can use that later, but it also still passes it to the if statement so it doesn't break it. But now we can use down here, for example, the matches variable. Oops, I should put a comma there so it puts a space between it. Matches, and then what we can do is from this, get the groups. So this is the capture groups that I was talking about a second ago. So these are all the things in brackets. This will return as a list, so we should be able to see that, actually. So go ahead and run this. Wrong one. String has no attribute matches. I think that's a very valid thing for you to argue, Mr. Python. To which I would counter, intriguing. Oh, I still put the dot in there a second time. That's very strange. Let's try that again and see if that was somehow causing our issue. Yeah, there we are. Okay, that makes much more sense. So here you can see our file name first, and then you have, this is a tuple, so those are kind of like your immutable lists, so lists that you can't change. And the first thing in it is our first capture group, and there's nothing else because we didn't have any more things in here. If we wanted also like the extension, well, it wouldn't really be terribly helpful, would it? Yeah, so that's fine. So here you can see we're getting our numbers, our gesture numbers. If we want to get them more specifically, we can index the tuple, just grab the first item out of it, square bracket 0, grab that, and voila, there we are. So it's extracting the number from the file name for each one of them, which is really nice. So now we have both a way to filter just the emoji data and get the gesture out of it, all in one step via the magic of regular expressions. Cool. Before I power onwards, how are people feeling about regular expressions? That might be a loaded question, or maybe not. Maybe you guys have all found it fine, and I'm the only person in the world who thinks regular expressions are scary sometimes. People feeling out. Oh yeah, they're also sometimes called regex, so I'll type that in, regex. Bring about regex in Python. And just kind of in general what we're doing as well. So any questions? Now is the time to ask. Or if you feel totally lost, let me know and I can think about how to help with that at some other point. Or maybe now, if it's easy. Cool. Okay, people held on there. That's good. Nice. It's a tricky one, these. But they're really, really useful. You can do crazy powerful stuff with them. In our case, though, I think it's time to start calling rand repeats. So one last thing that we're going to want to look at before we move on is how we stick this folder name at the front of this file name. So if you do it the natural way that you might think, just okay, stick the strings together with a plus operator, easy enough, right? Then you'll run into a little bit of an issue. Oops, there we are. So here you can see, aha, yikes. There's not, in fact, the slash that we need between final and EMG data in any of these. So you think, okay, easy, fine, that's okay. I can just put in a slash myself, right? And do something like this. And if we run that, then you can see, aha, okay, that looks much better, fantastic, wonderful. However, there's nothing saying that your user is going to leave off the final slash in final. It's just as valid to specify a directory by putting a slash after that as well. Uh-oh, now you have 2 slashes. That's a mess and a disaster. We could write a bunch of yucky Python code. Also Windows, though. Very good point, Kate. Windows uses backslashes instead of forward slashes. So, yeah, this kind of thing causes a whole bunch of trouble. If you want to not ever think about any of this that I've just shown you ever again, don't worry, you don't have to. Python's done it for you. That's also in the OS module. So we're going to use the function from there, os dot, and this is path, so it's the path part of the module, and then join. Then you just put the 2 paths you want to stick together. It figures out which operating system you're on, so if you need forward or backward slashes, and it figures out if there are 2 backward slashes and deals with that. It will figure out if there are none, and it'll add some where they're needed. Does all of it for you. Nice and magic. So we do path, and then file. We'll just stick together with our OS library there. Go ahead and run it. Hey, voila! Looks great, even with our trailing backslash. Now let's, just in case, get rid of the trailing backslash. Wow, still works. Someone on Windows, I'm sure. It should include backslashes for you. So it's a very nice way to do all these things automatically. So there we are. I think that's all the components we need. Essentially, these are the 2 arguments that we're going to pass now to our read repeats file. So let's do that. And I'd quite like to store all of the results of this in a list comprehension. I might be a person who overuses list comprehensions in Python. That's entirely possible, and I will accept that possibility. But for example, if we stuck here with like our for and our if loop, we would then need to add an empty list at the beginning, and then we would need to, on every loop through, do something like list.append. And I don't know. That just seems like a lot of faff for me, so we can do it as a list comprehension, since list comprehensions are meant to simplify essentially loops with conditions. So go ahead and rejigger things a little. We'll create a variable called all gestures, and this will store all of our different gestures, all the data frames from them that we've loaded from this individually. And we'll work a bit kind of backwards, not totally backwards. So we're going to say for the file in the path, so we're looping through all of those. Remember, list comprehensions are nice. You can put if statements in them as well. So if it matches our regex, which we can do, please don't do that. My keyboard shortcuts, I always get jumbled up. It turns out a keyboard shortcut for copying something in the editor that I use most of the time is the keyboard shortcut for exiting Spider. So that sometimes gets a bit exciting. Here we are. There we are. What do we want to do for all those things? So remember, the thing that you want to do comes before the for. So up here, what do we want to do with them? Well, we'd like to call the read repeats function. And our file here is going to be actually a combination of the file and the path. So we'll grab that there. And then our gesture number itself, well, that's going to be whatever we've gotten out of our groups that we've matched here. And we can do that. Wonderful. Toss away all of that. And then we'll have at the very end a return all gestures just so we can take a look at it. Now let's see how that looks. So in a list comprehension, run that, takes a second, takes a curiously long amount of time. Oh, it was probably just thinking about printing the massive amount of data. That's understandable, actually. Yeah, okay. So you can see EMG and gesture things. So, those are getting a bit crunched again. Let's see if we just grab one of those. So just the first thing from that big list that we are assembling. Yeah, still a bit yucky looking, but you do get your EMG data and your gesture number. They're a bit mushed up here. I'm going to show it in the terminal because it's terrible there. Preprocessing and data final copy. Zoop. Crunched. There we are. Much nicer. So there's your data. There's your gesture. That's the first item of that list. What if we look at the second item? Well, there you are. There's your next gesture. Different data. What if we look at the last item, which is actually gesture 3? Remember that, because it's weird. Last one will be 7. Yeah, so now we'll have gesture 3 here. All of the data there. Wonderful. Last thing we want to do is, instead of having this list of data frames, or which is fine, I guess, but a bit much, if you will, it would be nicer if instead of all of that, we had one big data frame with all of it smushed together, because that's fine, because we'll be able to record still which gesture's which by this column here. To stick all of these into one data frame, there's a lovely method for us to use called Kencat, for concatenating them all down into one data frame. So if we do that, that's in pandas. So bring back our favorite bears, pandas, and Kencat. Red pandas, bit off topic, but red pandas, they're just like raccoons, but red and also like cuter. They're ridiculously adorable. Look up red pandas if you ever need a an animal to enjoy, because they're adorable. Okay, here we are. Lovely. We'll go ahead and reload this. Uh-oh, SpaghettiOs. Is that something I was expecting? Maybe. I have left out something. I didn't know that it would actually create a crash, but maybe that's valid. Oh, of course. It's because I've done that. That's fine. There we are. Okay. So here you can see it's now working fine, actually. So we have our third gestures here at the end. We have our first gestures at the beginning. We see it's 231 rows, but what's this error is kind of hinting at is, we have 231 rows, and yet this is 29? 28? That's a bit odd. Let's take a look at a larger slice of that, if I can. I actually don't know if I can. From 0, I can't even do that, can I? If we use ilock, because remember, ilock always uses position, so that'll ignore weird labeling stuff going on. We'll go up through 35. There we are. So you can see, first gesture, everything seems fine. We count up to 29, And then, uh-oh, we start back at 0 again for the next gesture. That's not great. The reason for that is because, like I said, these labels aren't always the number of the row. And if you combine them in this way, it'll keep the original row titles. So it'll keep the original 0, 1, 2, 3, 4 from every single data frame that we loaded in. If we want to renumber all of these, there are a couple of ways of doing that, but the one easiest way is to hop over, and where we're doing the Kencat, give it an optional argument that says ignore the index and just renumber them. So ignore index equals true. Then what this should do for us is give it all in one giant giga data frame. Here we go. That'll do. There we are. Hey, now we're going all the way up to 230, which is good, because starting at 0, 230, that means 231 total things in it. So that's much better, and now, because 7 is actually a unique thing to ask for, was not before. Oh, actually, sorry, I'm being very silly. You can never look in data frames for rows with just a number. It always needs to be locked, doesn't it? But you can find individual rows like that one. Lovely. Cool. That is also, actually, I think, all of our loading EMG function, which leaves only one last function to go. If we look at the, well, if we look at how far we've come, which is a decent distance, I think, there we are. We have 1 giga data frame, every single gesture in it, every single repeat. Each repeat is 1 row, which is perfect, and for every 1 row repeat, which is 1 input, we have the expected output gesture, which in this case is gesture 0. Or down here, it's gesture 3, and all the gestures are still kept track of. All in one place, perfect for feeding into our machine learning, as we'll see next session. So now we have one last thing to do. Well, a couple of tiny last things to do. First of all is the data that we've collected here is at different lengths, which kind of isn't ideal. So to make that a bit more explicit, instead of just mumbling on about it, EMG 0. Here we are. Give me the shape of that. So dot shape is a way that you can see how big some bit of data is. So you can see here there are 8 channels, so it's 8 wide. That's fine, perfect, exactly what we would expect. But also, if we take a look at the second repeat, yikes, the second repeat is a different length. That's one's 114. And in fact, almost all of these are different lengths. So as we go through, even though they're somewhat consistent in like their timing, some other gestures, for example, might be much longer. It's like that one's 160. That's a problem for some particular networks. I think actually it causes issues for most. Some should be able to handle it. I remember when I was working with LSTMs, for sure, you want to be sure that you're feeding it the same window of time each time, so the same number of data points in time. So what we can do is pad things out a little bit. A common way to do this is find the average, or in my case, I'll find the median length of each one of these data sets. And for things that are shorter than that, put zeros on the end of it, or pad it with the same number like it's the last number or something. Just some space filler. And for things that are longer than the median, just chop them off. Sometimes this will cause you issues with your data, and you'll have to do some more advanced like rescaling stuff. In our particular case, this should be fine. Why is it fine? Because I've tested it. Lots of machine learning is a bit of trial and error at first, so it's definitely worth testing. But also because we made a point of keeping all of our gestures a similar time frame when we were collecting the data, so it's not like we're going to be cutting off half of the information or anything. Most of the information is still in that beginning first time bit. So that's one thing to deal with. The other thing to deal with is we'll want to transform our We'll want to transform our single gesture column into something called one-hot encoding, and I'll show you what that means in just a moment. So we'll have to see. We're running a bit low on time, but I think we should survive. So new function for shaping the machine learning data. This will take a data frame there, and we'll do some stuff with it. So let's see. Awesome. So first thing to do, find the median length. How are we going to do that? Good question. Well, we are talking about me, so it probably is going to involve a list comprehension. So let's start with that. First of all, let's put this in a little data frame here. Beautiful data frame, gorgeous. I just want the EMG column of that, because we're only dealing with this EMG column for the first bit of it. Beautiful. There's our EMG column. And it tells us, well, not actually. So each one of those will have a size inside of it. So we can loop through every one of those. So remember that we'll do with a list comprehension. And we'll call each one of those X, because I'm a creative human being. So for each X in this data frame, I'll print out the X so you can see this first. So here, it's just a list of these arrays. There's one array. Here's the next array. Here's the next array. Things like that. But remember, you can call functions on things list compression. So I can do on this X dot shape. There we are. There's the list of how long each bit of data is. So you can see most of these things are around like 119, 130. First one was 121, of course, and 114. So here are all these different lengths. Pretty typical looking so far. Now we can calculate the median of those. If we grab just the length part of things. So shape is a tuple. We can grab just the first bit, which is the length, since the second bit's all the same. There we are. We have a nice big list of how long every data set is. We want to find the median of that. Luckily, there's a way to do that. The statistics library in Python has a function for getting a median. And that's nice and easy, so we're just going to use that. So we can say from statistics, import median. And then on that whole set of data, you can just say, give me the median of these values, please. Et voila. The answer is 118. So that's about our average length. And if we look at that by inspection, that seems perfectly valid. Some of these are down in the 90s-ish. Some of these are down up in the 130s-ish, but they're all kind of hovering around 120, which is around 118. Awesome. So there we are. That is that. Just to double check. What is the type of that? Did I miss a bracket there? Sure did. Oh, it's an int. Okay, so that's fine. We might be able to get away without explicitly making this an integer. But sometimes, keep in mind, if medians have an odd number of elements, or, sorry, maybe an even number of elements, so there's not a middle of them, you can have issues with this. So, say I grabbed data frame all but one. Of course, again, there we are. See, now it's a float, and to demonstrate that without that extra layer of abstraction, it gives you this point dot 5 because remember, if you recall from doing statistics at any point, I don't know how many of you have, but I assume most of you have seen it. When you're calculating the median, if you have two middle values, you have to average the two. So sometimes you end up with something that's not quite an integer. But if we have something that isn't an integer, we're going to have massive issues. So we're just going to guard against that possibility by converting things to an integer, and that'll just chop off the decimal point, and that's fine. Awesome. But in our case, of course, without this artificial changing of the length, that'll still be 118. Cool. There's some data. That'll calculate the median length. Fantastic. So I'll call that the middle. And we can find the middle this way. Nice. And now we're going to get our data here. This is a bit of a squirrely bit, I will admit. So we're going to need to import some things here also as well. So we need to import statistics, which is what we just had. So from statistics, import the median. And also, something else we're going to grab is, and I'm going to copy and paste this because it is a really disgustingly long import, but it's from the preprocessing part of the TensorFlow Keras library, and it is called pad sequences. And what this does is exactly what I was describing earlier, where if it's too long, it'll cut it off, and if it's too short, it'll give it some padding. So the way we can show that off is, I'm trying to think about the best way to do this. I'll show it off one at a time first. So, well, yeah, I already have that on my clipboard. So we'll go ahead and copy this in. There we are. We have our pad sequences. It loads TensorFlow, whines about TensorFlow for a second. But it's fine. It's just telling me that I don't have GPU acceleration, which is, in fact, a true fact. Cool. So now what we can do is use this pad sequence function. So let's try that on just, like, one of our bits of data, for example. So what was a bit of data I had at some point? I had that. That's a bit of data. Yeah, there we are. And that has a shape to it. That's at 160, so this one needs to be trimmed by quite a bit, actually. So let's take this piece of data as just our X or whatever. There we are. And I want to trim it down a little bit. So I can use this pad sequences function. I'll show you how this works. So pad sequences, give it my data, and then give it the max length, which is an optional parameter. But we want to set a max length to be equal to our middle. I don't know if I've actually saved that, so I'll put in 118 manually, just like that. And this returns us something that we might not be expecting. If we look at the shape of this, actually, that's changed the wrong dimension to be 118. In most cases, when you're doing things like this, like in Numpy or stuff, you would have another optional argument, like axis. And you could say, okay, did pad it along this axis or this axis? And that changes whether or not it pads this dimension or this dimension. This particular function, for some reason, does not have that. But what we can do is spin around our data. So you can transpose data by doing .t. So if I do that and then do .shape of that, you can see it's basically just swapped the way it goes. It's now 8 things long, but each one of these lists is 160 long. So it's changed the shape of the data. And then what we can do after we've reshaped it, so I'll go ahead and show you this. So transpose it, reshaped it there. There you go. It's dropped down our 160 to just 118. And to get it back to how it started, at the very end, of course, we can retranspose it because that operation reverses itself. And we're back to where we want to be at our 118 padded. And if we take a look at what that actually looks like data-wise, there we are. Still 8 wide, as you can see, as we're expecting. But now it's 118 long instead of being longer than that. And if we had something that was too short, for example, so say, take something that was just half the size, so from 0 up to, well, really small, say, let's say 60 elements long. Take that, it's added a whole bunch of zeros to the beginning to make it the right length. So you can see all those zeros have been added, and the end effect of that is the shape is still exactly what we're expecting. Wonderful. Okay. Sorry for the slightly breakneck pace we're rolling on. I just want to get through this bit while we're still in time, and I'll be around a bit after time to answer questions, so don't worry about that if you have any. Cool. So we will do that. We'll also do it for all of the things that we're looking at. So we'll put it in another list comprehension. Boy, I cannot get enough of those. Pad sequences. Here we're going to take our x and transpose the x and tell it the max length is going to be equal to that middle value. That's our median that we calculated just up here. And then remember we want to transpose it back at the end so it's not all messed up. And then we want to do that for x in, and this is just everything in the EMG column of our data frame. So there we are. Let's take a look at what that looks like. Return. Run that. I'm trying to think if this is dumb. Yuck, it'll be fine. Go ahead and run this. It's loading in TensorFlow now. I can do my reverse search. Remember, Control R. And I want to grab load EMG data from folder. Nicely done. And load that into just something called, well, I had X before, data frame will do, so df. So there's all of our data again. And then if I push that through our shape function, so shape ml data through data frame, and voila, it spit out our list of all these things here, which are now correctly padded things. So all these should be the same size, which is lovely. So this one you see has some padding added at the beginning, these leading zeros. Now, one thing about this, if we take a look at the shape of that, that's a list that has arrays inside of it, so it doesn't even have a shape because shape is a NumPy thing. Basically, we want to take all of those things in that list and turn them into one NumPy array again. The way to do that is you stack them. So there's a function called stack. This basically turns this outer list, because if we look at like the type of it, for example, type, front row, type, that's a list. If we look at one of the individual things inside of it, that's an array. We want the whole thing to be an array. The way we can do that is taking our output that we have here and saying to stack it. So the function for that is numpy.stack. And then you just give it your data, and it will go and do it. So now you can see it started to do the thing where it's contracting the data again. If you look at the shape of this, it has a shape now, and this is perfect. This is just what we want. So we have it as 8 wide this way, so that's our EMG channels wide this way. Each one of these subarrays is the same length, it's all 118, and like before, we have 131 repeats of all of our different gestures. So that is our final input data, essentially, for TensorFlow. Fun fact, took me a year on engineering before I understood really what a tensor was, but it's incredibly simple. A tensor is just something like an array or a vector, but it can be in any dimension. So that's why it's called TensorFlow. This would be a 3-dimensional tensor, which is like, well, I don't remember what rank of tensor that is. That might be 2nd rank, might be 3rd rank. Somebody who actually knows what they're talking about should tell you that. But the point is, tensors are really just arrays with lots of dimensions inside of them. So heavily nested arrays sometimes. So here's an example of that. That's an excellent bit of data. Let's take that and export it or return it as one of our things. So let's remember there we had our data equals these sequences that we padded. What else did we do to it? We stacked it up to turn it all into one big array. So that's numpy.stack. Nice. And then eventually we're going to want to return that data. Also, however, I'd like to return 2 separate things from this function. I'd also like to return all of the gesture output things. But here's a bit of a catch. Machine learning algorithms work in just numbers, if you will. So, thinking. We'll load this, and we will load EMG from a folder. Yeah, go ahead and do that. And then here's your data final. Oop, store that in something. Data frame equals. There we are. Hello, file or data explorer. Here's our data frame. Gorgeous and hideous. So you can see it has all the nasty EMG data there, and then our gesture numbers over on this side, which you can see are counting up as we go along. The problem with this is if we give it just as one number, this gesture number as an output, that's what our machine learning will try and give us. It'll try and give us like a 5 if it's the 5th gesture, or a 6 if it's the 6th gesture. But what if the algorithm isn't really sure? What if something looks a little bit like gesture 6 and a little bit like gesture 7, right? So, okay, maybe you can guess, it might give us 6.5. That's halfway between the two. That makes perfect sense. 6.5, cool, great. What if, however, the gesture ends up looking a little bit like a combination of 7 and 3? What do you do then? Well, okay, maybe if you have 7 and 3, you again do the thing where you sit like halfway in the middle of the two. So let's see, what's the gap between those? You have a gap of 4, so you might pick 5. But wait a minute. If you pick right in the middle of 7 and 3, which would be gesture 5, then that is indistinguishable from just saying, well, I'm certain it's gesture 5. So how do you know if it looks like 7 and 3 or just like gesture 5? So you can see there's some ambiguity here. And there's a really easy way to get rid of that, and it's called either dummy encoding or one-hot encoding. I've heard one-hot more often. Pandas calls it dummy encoding, and I'll show you what that looks like. Essentially, what that does, in fact, I'll show that off here. Data frame. Gorgeous. And if I want to just look at the gesture column of my data frame, gestures, there we are. Beautiful. So we just have our numbers in there, and we want to convert those into something that helps resolve this ambiguity. Well, let's try dummy encoding it, and you'll see what that is in just a second, and I'll explain why it looks that way. So git dummies, and voila, we have something like that. Now, what this means, and you might have already cottoned onto it if you're being observant, which I'm sure all of you are quite observant. I'm going to do that in the Data Explorer so we can see it there. It's a bit nicer. Hop over here and take our, well, actually that should be the exact same line of code, and store that in labels. So that's labeling our data with which gestures that it is. Cool. All right, so here is our big thing. If you've already guessed how this works, well done. It's pretty simple. the idea is it takes numbers, like before we had numbers 1 through 7, it turns each possible value that column could have into its own column. So we have here a 0, a 1, a 2, all the way up through 7. And what it does is whenever it is one of these things, it will mark it with a 1. So here, all of these are gesture 0, so gesture 0 is full of 1s. Once we get down to this part, you can see from 30 onwards, so 30 repeats of 1, now 30 repeats of another. This is now moved to being gesture 2, which is in the second column, and then it'll do the same over here. We can move to this column, and then we jump all the way to that column because it's a little bit out of order, then this one, then this one, then that one, then we jump back to 3. But you can see that we've gotten rid of our ambiguity now. So now, what if something looks a little bit like 7 and a little bit like 3, but you don't pick 5 anymore. Instead, you can put 0.5 in 3, because it looks halfway like 3, and 0.5 in 7, because it looks halfway like 7. And there's no longer any ambiguity there. And this is how most categorization neural networks work, or machine learning in general, for that matter, I think. When you're categorizing something, if it can kind of blur the lines of a category, it's very useful to have it one-hot encoded, or dummy encoded, like this. It removes that ambiguity, helps the computer be much better at training the algorithm. Wonderful. So the last thing we want to do then is, in addition to returning our data, we also want to return that dummy encoded thing. So we'll just toss in that little bit. So that is labels, and that'll be this here. Oh yeah, and one last thing about that we can do. This here, as you can see, it says the type of this is a data frame. That's fine, that's dandy, I guess. But having columns named 1 through 7 and rows named 1 through however many there are, that's not very helpful. We don't need that. We've gotten rid of it for our other things. So you can do dot values, and that gives you only the values of the data frame kind of thing. And here you are. We're back to getting a NumPy array where we have all the things we need up here, starting, well, so it's basically, it's the same data, but now as a NumPy array without those extra column and row labels. So we'll go ahead and return that, because then we'll have one NumPy array for an output, one NumPy array for an input, and TensorFlow really likes dealing with both of those. So dot values, dot row. And then we want to return the data and the labels as two separate things there. So now when we go ahead and run all of this code, the first thing we'll want to do is load in our EMG data from our folder. So we want to put that in something called data frame. So there we are. There's our updated data frame label. And then what we can do is get data, comma, labels. Remember, you can break up tuples like this. And then we want to shape our machine learning data from our data frame. Et voila. We can now see that data is an array of, or a NumPy array of 32-bit integers. And if we take a closer look at that, that is, in fact, our NumPy array. In fact, this is really cool. You can see the patterns in this a little bit as you go along. So here we're just looking at the first gesture, first repeat even, but here are the columns, here's time, and you can see the colors changes, the numbers and the cells change, so you can see there's a very distinct pattern when the fist is clenched there, which is kind of cool. Awesome. Labels, there's our other array, and this is just our array of dummy encoded things, where you can see, there you are, definitely gesture 1, gesture 2, and etc. Lovely. Load in the weird order where 3 is last for some reason. Fantastic. That is all the pre-processing. Once we get to next week, which is where we'll actually be talking about the different models and things, basically, whether it's an LSTM or a convolutional neural network, which we'll probably try and go over a little bit of both, you just toss it this labels data and this input data, and it will learn best it can off of that. So that is our pre-processing just about done. Well, actually entirely done, at least for what I did. There's always more you can do, though. So, seeing as I finished this with 20 seconds to spare, I understand if people need to scurry off, but also, I really accelerated near the end there, and I'm going to be around for as long as people need for questions. So I'll ask, how are people feeling overall? And please do ask questions in either the Discord or the Google Meet, and I am happy to answer. Best I can, anyways.
Can I just ask a question verbally?
Yes, you may.
Because I have to leave in like a couple of minutes.
No worries at all.
Sorry, I was dropping in and out because I was working. I think I might have missed it at the start. But did you use it looks like you used all of the data for training data.
Yeah, so I've actually not split up the training data into training and testing data just yet. I'm processing all of it the same way. Once we get to, I was planning to do that next week when we're feeding into the neural network. At that point, yes, you do want to do something, as Kate's been pointed out, you want to split it into testing and training data. So, and the training data is something that, or sorry, the testing data is something that your algorithm doesn't see until the very end after it's already been trained. The reason you want to do that is because if you just give it this data, and you have a powerful enough network and you tell it train on this, it'll eventually just memorize all of the patterns. It'll be 100% accurate and an entirely useless neural network because the second it sees real data, it won't be able to pick out the general patterns or whatever. So we'll go over that, yes, next week, but we do end up splitting it up.
So this block is all of your data.
Yes, yeah. This so far is all of the data in general. And then we use a nice little function. I think it is from scikit-learn maybe. It randomizes it and splits it into 70-30% split for testing and training, I think.
Okay, cool. Thanks.
Very good question. Awesome. Cool. Any questions from other people as well? Anything that I glazed over a bit too quickly there? Cool.
I thought it was really good. I really appreciated how unlike some of the other seminars and workshops I've been to from societies, you actually like talked through every step you were doing instead of just telling people, okay, type this, now type this.
Yeah,
a lot of the AI ones in the past used to be like that, and people would walk away being like, okay, well, I completed the exercise, but like, why was I typing what I was typing, you know?
Yeah, that's good. That's why I tried to dry this one out over 3 whole things, because we could, if we did it that way, probably compact it all into one session, but I figure it's more helpful if people actually understand what they're doing, because I had to figure it all out, so I figured it'd be easier if I didn't force you all to do the same. I actually just told you something useful. But yes, awesome. That's good feedback. Cool. Speaking of feedback, I've forgotten to make this week's feedback form, so I'll send that on the Discord later. But if you're feeling good and you don't have any questions, feel free to take off. It was lovely having you, and I'll see you back here next week for when we're actually talking about giving this data to neural networks. This was like the hard kind of like boring part that we did today, but with all of this done, next week we'll start getting to the exciting bits. But yeah, I look forward to seeing you then, and I'll stick around if anybody has any questions. Yes, hopefully that's very helpful. Yeah, thanks for all coming along. Lovely seeing you. Cool, I could probably stop recordings as well.